Hey everyone, so we just finished talking about all the different types of energies with the exception of spring potential energy. Next thing we're going to talk about is a little thing called power. This is going to be actually a very quick comment. This isn't going to play into a major part. It's just kind of something that you have to be aware of. Uh, Power in this unit is represented by the symbol of a capital P. It is extremely important that you keep this as a capital P and not a lowercase p, because a lowercase p is a completely different equation and measurement. So before I give the definition of what power is, the question I want you to think about is, what would a person need to do to be seen as powerful? Now, a lot of people will probably say something like, oh, the more power means they're very strong and they can move a lot of weight, or apply a great amount of force if you want to use concept of physics. However, it's important to keep in mind that power also considers how fast this is being done. A good example of this is, think about who is stronger, a person who takes an hour to push a car or a guy who pushes the car in a minute. Obviously, both of them are able to apply the same amount of or a similar amount of force because they are both able to move the car. However, one of them is doing it much faster than the other. So the one who did it in a minute would be seen as much more powerful. So time is going to be taken into account as well as how much force is being done. So the scientific definition for power is that it's the rate at which work is done. So it's how quickly we could do our work. So power is related to the work we can do or the force we can apply to move an object in addition to the amount of time. So the greater the force, the more work we do, as well as the shorter amount of time, the greater the work. So the equation will be written like this: P equals delta E over delta T. Uh, the unit for power, so 1 unit is actually joules per second. So energy is going to be in the unit of joules, time is in the unit of seconds. However, the other unit for power is watts, capital W, W-A-T-T, watts. And there are other equations that we now have for power with this. So some of these equations are not going to be on the AP reference table. I think the AP reference table only has this. The regions reference table does have the other variations, but it's really just playing around with the equations that we already derived in the previous part. So for example, we know that delta E is equal to work and FD, and we know that V is D over T. So the other forms of this equation could be, I can replace the delta E with W. So work divided by time would also be power. I can replace the work with FD to get FD over T. I can replace the D over T with V to get FV. These are all different variations. Another thing to keep in mind is that because we say that work is a change in energy, if the energy is gravitational potential, so we're lifting an object up, then we could replace work with UG or delta UG. If the object is getting faster, so it's changing its kinetic energy, we replace work with delta K. Basically, the idea is that this power equation is very versatile. It's very flexible in what you want to work with, depending on the scenario. So just keep that in mind that there are a lot of options to this equation. Um, they all mean the same thing. A lot of times you'll see the equation on the regions reference table written like this to kind of say that power can be equal to any of these other three terms. But like I said, the AP reference table strictly has it written like this and assumes that you can derive the other forms from this. Um, so let's do some practice with it. Pause video, work self, and we'll go over in a second. All right. So we just use our equation. We're given a force, we're given time. So let's see, we do 300 times the displacement of 6 divided by 20 seconds, and we end up getting 90 watts. One thing to keep in mind is we do still have to take into account the fact that this is supposed the force and the displacement do still have to be parallel to each other, so they have to be in that same plane. In this case, we're moving the crate, we're exerting a push and pushing it in that same direction. So I don't have to worry about the cosine theta. But if the force was being put at an angle, I would have to take that into account. Here's the next question. Pause video itself and go for a second. All right, again, just plug and chug. Because they're giving us a speed, we're going to use the speed version. Power equals force times velocity. The force here, because we're lifting the object up, again, is going to be equal to the weight of the object, where we're balancing the force of gravity. So it's going to be 1,000 times 10, and then times that by the 8 meters per second, and we end up getting 80,000 watts. And that's it. Like I said, power is a pretty small thing. It's just something that you kind of have to recognize that it's there. Sometimes it can be used as a way of finding work. So they might give you some numbers of power, and then you would use that equation to figure out what the work is. To that would then lead you on to other parts. Or at the very end, they just kind of like tack that on as another part and say, "Oh yeah, by the way, what's the power?" And again, you just use the equation, work divided by time. Like I said, it's nothing really major. The other equations are going to be a much bigger part in this unit. So keep that in mind. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.